office 049. So anytime you can send me an email, you can come, no problem, okay? We are going, as a background, I'm a chemist, in particular polymer chemistry. So I use homogeneous, in the past I've used also heterogeneous catalytic systems for the synthesis of polymers. Today we are going to see mainly the group 4 from the periodic table, which is the titanium zirconium and hafnium polymerization. They are, let's say, the most popular one, most used one. So the content of the lecture is, let's say, divided in two parts. The first part would be on the Ziegler-Natta catalyst. So it's an heterogeneous process. And we're going to see the stereochemistry of one alkenes and stereo and regioregularity. So where it comes from, how the alpha olefin can coordinate, and the consequences on the polymer. And a bit of the Ziegler-Natta catalyst itself, so how it's formed and different generations. We will have about 5-10 minutes break, and then we start with the homogeneous part. We will see this later on. So, first of all, the stereochemistry of poly-1-alkenes. So, this is the reaction, various reaction. You start from an alkene, and you open the double bond, and you create the polymer. So, what we are not going to look at the reaction itself, but we focus our aim on the catalyst. So, just a bit of background. This is a very highly exothermic reaction, so it produces a lot of heat, which you have to remove in your process. Industrially, the polymerization are run around 80 degrees, and some of the reactions are very exothermic, so you have to keep the temperature at 80 degrees, but it's not particularly difficult because the reaction itself is very isothermic. So, according to which is your R, which is this group here, if it's hydrogen, is the normal polyethylene. You can have also, these are the mainly one, the most popular one. If it's a methyl group, you have polypropylene. If it's a methyl group, it's a polybutene, or polystyrene, it is a normal. The monomer, this is the monomer. If you have an R different from hydrogen, it is a prochiral monomer, which means that it will form a chiral center. So your polymer that you produce can have different stereoregularity. So your methyl group can point, let's say, in one direction or another direction, and very general. If it points in the same direction, we call it isotactic. If it points one time in one direction, one time in the other direction, or is, let's say, RS, RS, RS configuration, then we call it syntactic. Now for polymer, if I ask you, is this center here R or S? We are not really capable to give an answer because we should give priority according to the rules. How can you give priority if you don't know how long is this chain and how long is this chain? So it's very difficult. So that's the reason why we generally use this kind of representation, which is the Fisher representation, or we should say adopted Fisher representation, because we omit divergence. And it's a relative configuration. So what does it mean? It's a relative according to the previous, if it's a polypropylene, according to the previous methyl group. So if the methyl group points in the opposite direction, then we call it R. If it points in the same direction, then we call it N. Okay? So basically, if you look at the atactic here, so this one is our reference. This methyl group points in the opposite direction, so it's going to be an R. This one points in the same direction, so it's going to be M. Opposite direction, R, and so on. Okay? For the isotactic polymer, which points in the same direction, we have a string of M. So this is your stereoregularity. Okay? If your polymer is syntactic, it's going to be pointing always in the opposite direction, so it's going to be a string of R. A bit of history, a bit of background. So everything comes from the Aufbau reaction. So the discovery of the Ziegler-Natta catalyst comes from this point here. The gentleman there in the picture is Karl Ziegler. He was studying, a German professor, he was studying the Aufbau reaction, which is the oligomerization of ethylene in the presence of aluminium alkyls at very harsh conditions, so high temperature, high pressure. And in this process, he was producing oligomers, which means very short chains, around 10, 20 carbons. And suddenly, you are expecting an oil in your mixture, and you get some white powder. Something went wrong, or very good in this case. So what happened in that case? The previous scientist that was using this is the original reactor, was using the reactor, used titanium chloride. And the reactor was dirty of titanium chloride. By using the aluminium alkyl in combination with the titanium chloride, he produced the first catalyst for the olefin polymerization. So this is a schematic representation where you have your titanium chloride, which can react with aluminium alkyl to get the active site. We will see this later in details. And here you can have your polymerization. So if you increase the length of the chain, so you go from oligomers to high molecular weights, the polymer precipitates in the form of powder, white powder. And this is, let's say, the first probably synthesis of high molecular weights PE using this catalyst. Then comes here a second gentleman, which is Giulio Natta, an Italian researcher, which he has extensively studied the synthesis of PE, but mainly PP, polypropylene, using Ziegler's catalyst. And he found that the titanium chloride has different forms, which is called polymorphism of the titanium chloride. So you have different forms. Each form has consequences in the stereoregularity of your polymer. And by the four forms are here written, the alpha, beta, gamma, and delta. As mentioned here, the violet is the most used one and has high activity and higher selectivity. So let's say by the combination of these two, the work of these two, we end up with the Nobel Prize in the 63, if I remember, yes. That's a pretty good reason to why we are here discussing about this. If it's not enough for you, this is an estimation of the production of PE, PP in 2005, which is about 47 billion pounds, which is really a lot. So it's a huge production. There is a very big market, and it's not decreasing. Although we now are starting with the bio-based polymers, this kind of products, PE and PP, are still extensively produced. So I would say it's a good reason to keep studying this kind of class of material. The accredited mechanism for the polymerization, the Tosi-Harman, I think we have already seen this, but we can see in detail here. Here is a reference if you wish to have more information. We start from the active site, which is a cationic titanium in this case, bound to an alkyl group, which is called R in this case, can be methyl, ethyl, and you have a free coordination site, where your olefin, in this case ethylene, can coordinate the titanium. Then you form a force center between titanium, your alkyl group, or chain if it's already polymerizing, and your olefin. It's a force center, so it's quite tight. So there are only 4 atoms involved in this center. And then you have the insertion. So if you see, it's very important, you have the vacancy here and the free coordination site here. So you have 2 different coordination sites, which means that the olefin will coordinate once here And for the second insertion, this is very important. We'll see later on why. This is a video of the Gaussian-Arlen mechanism. I hope it works. So you start from the titanium with an active group, as we mentioned it, and this is the free coordination site. So the olefin will coordinate the titanium over the orbital. So the titanium is cationic, so it wants to attract as much as possible electron density, and the olefin contains some electron density. So you have the coordination, then you have the insertion with the 4 center. Then you have this sigma bond which is breaking, and this one's called. Then your chain rotates and frees the other coordination site. Then it keeps going on. Second order come, coordinates, form the transition state for center. And then freeze the second coordination site. And this repeats many times. So, stereo and regular regularity of the alpha olefins. So we have an alpha olefins. In this case, this is the propene. We have a methyl group here. It's one monomer, but I can coordinate the active site in 4 different fashions. In this case, we have the metal here, general titanium, your drawing chain, and this is your olefin. This is the C. The olefin is coordinating the metal with the C phase. You are familiar with C and ray phase, right? No, okay. So your olefin is prochiral, which means that has 2 phases, is flat, and has 2 phases. If it coordinates with one phase, it will point the metal in one direction. If it coordinates with another phase, it points metal on the other direction. How can we understand if it's C or ring? Try to imagine yourself sitting on the metal. So you are looking at the olefin in this direction. And you have to assign priorities. So the priority number 1 will be on this carbon here, then this carbon here, and then the hydrogen, right? This is your prochiral carbon, which will become chiral. So this is to go from 1, 2, and 3, you have to go looking at this direction is clockwise, but because you're sitting on the metal, it's going to be counterclockwise. Do you all see it? So you sit on the metal, so you're looking in this direction, and you count going from 1 to 2 to 3, it's going to be counterclockwise if you look from the back. That is the C phase, if it's counterclockwise. If it's clockwise, it's the ray phase. It's okay? Would you like me to repeat? Yes? No? Yes?
Which one was which again?
So, try to imagine yourself sitting on the metal.
No, I got that. It's like the counterclockwise.
So, if it's counterclockwise, it's the C. If it's clockwise, it's the ray phase. So, you can have 4 different ways to coordinate the metal. 2 of them with the metal pointing up, left and right. So it will be the C phase and the ray phase. And 2 different coordination where you have the methyl group pointing down, left and right, which will be again the ray phase and C phase. Does it really matter? Yes, it is. This is, let's call the carbons. So this is carbon number, I don't know if you can see it, maybe it's too small. Carbon number 1, 2, and 3. Recalling the Cauchy-Arlen, this one will bound this one. Carbon number 2 will bound this carbon here. So you will have this sigma, sigma bond, sigma bond, sigma bond. So it would be a 1-2 coordination. Okay? If it's the other way around, with the metal pointing down, it would be a 2-1 insertion, which means carbon number 2 will bound to the metal, carbon number 1 will bound to the Groving chain. So this is a different kind of insertion. So it's going to be, in this case, secondary 2-1 insertion would be a Regio error. If the metal points in one direction or another direction, you will have or the R or the S configuration over your chiral carbon. So if your active site inserts only in one way, your metal, always with the primary 1-2 propene coordination and the C or ref phase, always C or always ref, is going to be isotactic. Let's see. If your olefin is coordinated once with the C phase, once with the R phase, with the metal group pointing always up, then it's going to be synotactic. Okay? We will see this later on anyway. So this is a schematic representation of what can happen. So if your site is non-selective, so your metal group can be up left, up right, bottom left, or bottom right. So there is no stereoselectivity, no regioselectivity. Your resulting polypropylene or polyone-alkene will be stereo and regio irregular. And this is more or less what happens. So your alkene will be once up, once down, or once R, once S, without any regularity. And you will have a 2-1 insertion. So this is a 1-2 insertion. This is a 2-1 insertion. Okay? We will see later on in detail. If your site is regioselective, which means that the metal group is always pointing upward, but there is no stereoselectivity, which means that your metal group can be pointing left or right, it's going to be regio-regular because your metal group is always up, but stereo-irregular, which means that once is R, once is S, randomly distributed. And we call this kind of polymer atactic. If your site is regioselective and stereoselective, which means regioselective metal group pointing always up, and stereoselective, which means that your active site can differentiate between R and S phase of your one-alkene, you have a regio-regular and stereo-regular polymer. In this case, it's called isotactic. Is it important? Yes, indeed. Everything is important. Your properties of the final polymer will be dependent on the regio-regularity and stereo-regularity of your final polymer. So the higher is your stereo-regularity and regio-regularity, higher will be your crystallinity, for example, your mechanical properties, thermal properties as well. Now, if your active site is capable to differentiate between R or S, means that somewhere there is stereo regularity. So your active site at a certain point is stereo regular, or at least rather than stereo regular is stereo selective. Okay. Now this is a schematic representation of the Ziegler-Natta catalyst. So we will see later this. Here is magnesium chloride, where your titanium can coordinate, and the titanium will coordinate the chlorine, which are coordinated to a magnesium in an octahedral distorted octahedral configuration, which means that you can have two different kind of active sites. If you look from the top, I think they have done this kind of representation, right?
At delta, no, we haven't looked at.
Okay. So if you look from the top, this looks like an helix. So if your helix would be, again, clockwise, is the delta. If it's counterclockwise, is the lambda. So these are mirror images, which means that you cannot overlay each other. So once we'll take the R phase, once we'll take the other one, will take the S phase, the C phase of the problem. Okay. So because of this, the active site can discriminate between R red phase and C phase of your prochiral monomer. Okay. Is it clear? Would you like me to repeat? Yes. Okay. If you have octahedral geometries, so this goes above the board, and this goes into the board, and you have at least two bidentate ligand. You can have two different possible configurations. This one, if you look from top, you will see a clockwise helix or mirror image. If you look from top, your helix is going to be counterclockwise. Okay? One is called delta, one is called lambda. So, if you coordinate your olefin here and here, this is still delta, that one is still lambda, and it can discriminate between the R red phase of the one alkene is coordinating and the C phase. Okay? So this is your source of stereoregularity on the catalyst. Where is your bidentate ligand? Is the chlorine, which is connected to a magnesium in the crystalline structure of the catalyst itself. So you have to look at this like a bidentate ligand. So this is going to be delta, this one is going to be lambda. Okay? So because there is stereo select, it's, let's say this metal here is coordinated with two bidentate ligand in a delta fashion, it will take one preferential phase of the propene. Be better? Be more clear? So how this is transferred to the monomer. This is more or less the same representation. So you have your metal, your chlorine connected to the magnesium. So this is your bidentate ligand, this is your bidentate ligand. Once the polymeric chains start growing, it becomes quite big. So it has to point in one direction, right or left. So here, there will be something, chlorine, or we will see later on a donor, which means that this group here will point the chain in one direction. Okay? This is your olefin coordinating the metal. Now your olefin can point your methyl group on the left or on the right. Where do we point the methyl group? It depends on the chain. If the chain is on the right hand side, because there is a group there which points the chain in one direction, then this part of the quadrant here is predominantly occupied by the chain. So the methyl here would be less probable, and it will point in the other direction. And this is your source of stereoregularity in your polymer. So let's say these two different sides, A and B. In case of A, your chain is pointing in the right side. In the case of B, also pointing on the right hand side. But the monomer here is pointing on the alkyl group here is pointing on the left hand side. The alkyl group here is pointing on the right hand side. This methyl group here is going to be sterically demanding, and here there is your chain, which will push away the methyl. So this is less favorable compared to this one. Okay?
I have a question.
Yes.
If there's a group bonded to your MG and the right, doesn't affect also the
This one.
yeah.
In the second insertion, this is the first one, let's say. In the second insertion, your chain will be here. Okay? Here there is something, indeed. Which means that your chain, in this case, is not going to point here because there is something here, but it's going to point in the opposite direction.
So it's going both influences by
Yes, correct. We will see later this in details. So this is for one insertion. We have seen in the Cauchy-Harman mechanism that it is important what happens in both coordination sides. So in one case, there is something here which points your chain on the right hand side. After the insertion, the chain will be here. And after the first insertion, there is something here which will point your chain here. And the methyl will be pointing in that direction. So yes, it is important and it affects. We will see later this. Now, what do you expect if the first monomer, monomer insertion is stereoregular or not? So we have said, I repeat, the chain will affect how the methyl group is oriented, if right or left. So if you are starting your polymerization, so you don't have yet the chain, what do you expect? The first monomer is inserted in a stereoregular way or not?
no, right? Because you don't have a chain to orient.
So the first insertion, you're right, would be 50% R, 50% S. Then while the polymer grows, it will orient the methyl group, so your stereoselectivity increases. Correct, very well done. And okay, we have seen how the methyl group is oriented, but why should be always up or why always down? Two reasons. One is the steric repulsion. So we are looking at the catalyst from the top, okay? So the blue is your prop E, and the red one is your drawing sheet. Now, if you're, let's say, here is where the methylene is. Your methylene will be here, okay? If I point in this direction, your methyl group is going to point towards the catalyst. So it's less favorable because it's steric repulsion between the methyl group and the catalyst itself. So it's energetically more favorable to have the methyl group pointing in the opposite direction. Okay? That's one. Second, electronic. These two carbons here are sp2 carbons, which are a bit more electron rich compared to sp3 carbons because of the full p orbital. Now, between these two carbons, this carbon here, carbon number 2, will be a bit more electron poor compared to this one, because the sp3 carbon will attract a bit of electron density. Okay? So there is a small delta plus and a small delta minus between these two carbons here, which are not exactly the same in terms of electron density. For the metal is quite easy. There is a cationic this is a cationic species, so it's a delta plus, and there is more electron density on the carbon, which means that you will have two dipoles. We know that if you point the dipoles in the opposite direction, this is a more stable configuration compared to having the dipoles pointing in the same direction, okay? So this is the electronic source of stereo regularity as well. Now, let's see which are the consequences of this stereo regularity over your chain that you have produced. Whatever you are producing and whatever the catalyst does over your chain, you can understand what happened during the catalytic process by examining the polymer itself. Let's say we say that the microstructure of the polymer is basically the fingerprint of the catalyst. So what the catalyst imposed over the monomer and then in the end over the chain, you can understand by characterizing the polymer, okay? So let's see the top one. These are microstructures of isolated stereo defects. So sometimes, yes, your chain will point the metal group always in one direction, but sometimes it doesn't. Or at least you give enough energy to make an error, okay? It happens. It's an energetical driven process, so it can happen. And how your polymer looks like. So if it's an isospecific polymer, which is isotactic polypropylene, you will have always your metal group pointing in the same direction, and suddenly, stereo defect, it happens, and then it keeps going always in the same direction. Using the Fisher representation, we can say this is a string of M, and then two R's. Okay? So, stereo defect is metal group pointing in the opposite direction. Then, the catalyst, let's think I am the catalyst. I've done a mistake. I have to correct myself. Then it keeps going always up. Okay? So you can understand your, let's say, if you look at the pentadiscs, which are 5 metal group, you will see something like this. So it's a classic stereo defect, MRRM. Okay. So string of M, mistake, R. The site corrects itself, another R because it points up, and then M. In the case of single specific polymer, which means that you have once pointing in one direction, once pointing in the other direction. So it's RS, RS, RS configurations. You have this kind of string of mistake, let's say. Here it happens a mistake. So instead of, let's say, let's think that this is R, so it's going to be RS, RS, R. Here should be S. It makes a mistake, so R. Then corrects itself. Again, RS, RS, R. So this is the classic string of single specific stereo area. Okay? What is this? So first of all, what do you think this is? This is a string of M, which should be isospecific. Okay? But if you look at the configuration, let's think when it points up, it's R. So it's a string of R and then S. A string should correct itself and then going always up. Another example for the syntactic polypropylene. This is a string of R. Okay? So syntactic. It makes a mistake. So M pointing in the same direction. And then it does not correct itself, the site. And it changed the configuration. So here there is a different source of stereo regularity. It does not come from the site itself. Where it comes from? The answer is here. So again, we go back to the site, to the active site. If your catalyst with the bidentate cannot induce stereo regularity. What else it could be? There must be another source of stereo selectivity. What else is, where do you see a stereogenic point? Can you see?
On the chain.
On the chain. This is a chiral group, okay? So if your catalyst, sometimes depends on the catalyst structure, cannot give the right stereo selectivity, or let's say you are giving a lot of heat, we'll see this later, what it can give stereo regularity is the chain itself, okay? So in that case, once it occurs a mistake, so instead of this go back, it makes a mistake. It's not the site that controls the stereo regularity, but it's the chain. So the chain says, okay, now you have to always produce the polymer with the same configuration, because the mistake happens here. So if the chain says I want always R, then it happens a mistake. It's S. The chain wants always S, so it's going to be always S. Okay, is it clear? Would you like me to repeat?
Does that mean that like the catalyst has no influence at all in this case? It's like just the chain?
Not on the stereo selectivity. Okay? So you can understand these things by looking at the chain, so at the polymer. So you understand the source of stereo regularity if it's a chain controlled or site controlled stereo selectivity by looking at the string, at these strings. So this is a classic MMRM or MRMM, a string of chain controlled polymerization. MRRM or RMMR are the classic examples of site controlled polymerization. How can we determine the microstructure? Via NMR, carbon-13 NMR. Now, what is this polymer? Which is the predominant peak here? This one, if you see it's out of scale. And it's an MMMM polymer, okay? So it's a isostatic or synthotic? Isostatic, correct. And this is a site-controlled stereo defect, okay? So we can see these small peaks here, which can be attributed by there are some works in the literature where you can understand a specific values of ppm, which is the string that corresponds. So let's examine it. If you have these MMRR, it will be visible here. Okay, guys, bear in mind, this is out of scale, so these are very small peaks. They can be easily confused with background noise. So the carbon-13 that we are acquiring here is very different from what you may get used to. So generally, this you have to acquire really lots of scans and have particular care while you are acquiring the spectrum. So these are generally acquired over hours, not half an hour, which generally we are used to. So you can have the string of MMRR, which is this one, the string of 3M and 1R, this one, and MRRN. In a ratio 2 to 1 about these strings. Why 2 to 1? This is asymmetric, so it can be 3M, 1R, or 1R and 3M. This is also asymmetric, so MMRR or RRMM, and this is symmetric, so it's going to be only MRRM. That's the reason why the ratio between them is 2 to 1. Which is the concentration in terms of stereo defect. How can we say it's 0.5% stereo defects? Let's compare with the carbon-13 satellite peak. So this is something which you always have, independently of what you are looking at. this is the abundance of the carbon 13, depends on the abundance of carbon 13, and is the probability of having two carbon 13 next to each other, which is about 0.5%. And that's how we can determine the amounts. It's not always the case. Generally in carbon 13 we used to say it's not, you cannot really understand which are the amounts of the peaks, so the intensity, you cannot determine intensity. If you take some precautions, you can. If you would like to know more, this is, let's say, the article for the microstructure of the polypropylene. I would suggest to have a look in case you are interested. What about the rigid effects? To recollect, rigid effect is when the metal group is pointing down. So, and this is going to be inserted in a 2-1 fashion, okay? So you are expecting your metal group here, but because it inserts in 2-1 fashion, your metal group is going to be very close in alpha to the stereogenic point. So this is your string that you are going to see in NMR, and you will see something like this. So the metal groups, which is a metal group which is next to another metal group and CH, but not metal. It's a CH2 close to another CH2 and a CH that will resonate different according to this CH2, and you can see this here. Okay, so that's how we can recognize the rigid effects. Now, some words about the catalyst itself. The first generation we have seen is the titanium trichloride activated with aluminium marking. This is the first catalyst discovered, and it is quite low productivity. So it's about 1 kilogram of PP per gram of titanium. I know you are used to different kind of productivity, which is ton and TOF. But here it's very difficult to determine the number of active sites because we don't really know the number of active sites. We have different kind of active sites, and not all the time the amount of titanium is active. Actually, it's the other way around. A very small percentage of titanium is active. So we don't know. It's difficult to understand which is the turnover frequency or the turnover number. And that's why we generally see kilograms of polymer produced per gram of catalyst. Then the second step of, let's say, second generation comes from a very simple thought, which is why using titanium and waste all this, let's say, in the first generation, this is all titanium. It's wasted. It's inside the bulk, okay? And it's wasted. So why use titanium? Can we use something different? It turns out that magnesium chloride can be used, and it's pretty good because the titanium can epitaxially grow over the magnesium chloride. What does it mean? The magnesium chloride and titanium chloride have a similar crystalline structure. So the titanium chloride can easily sit over the magnesium chloride. Okay? Simply by supporting the titanium chloride over the magnesium chloride, we can improve productivity, which goes to 5 kilograms of PP per gram of catalyst, and also the isotope activity. Now, a word about the polydispersity. Polydispersity is when you have a polymer, you don't always have a certain molecular weight. You have always a range of molecular weights, okay? The polydispersity index gives an idea on how many chains you have, or rather than how many chains, the distribution of the molecular weights. So if it's a broad molecular weight distribution, it means that you have a very broad range of molecular weights. Okay, so you can have very easy example. Let's say you have 10 chains. Okay, if 7 chains have a certain molecular weight, let's say molecular weight 1, then 2 chains molecular weight 2, and 1 chain molecular weight 3, you have a certain distribution. If you have another example, 10 case with 3 chains of molecular weight 1 2 chains, molecular weight 2, 2 chains, molecular weight 3, 2 chains, molecular weight 4, and 1 chain, molecular weight 5. Your distribution of molecular weights is going to be larger here compared than here. Okay? Very simple. Why you have a distribution? It's the chain can be cut according to the condition you are using. So if generally, as I say, at 80 degree, you are giving a lot of energy. So the site can cut the chain randomly according to the energy you are giving. So it does not cut the chain always at the same time. Another source is a different kind of titanium which is over the magnesium chloride. Because the magnesium chloride has different cuts, different phase, you have different crystallinity patterns, and the titanium can sit over these different patterns. You have different species, which can give different kind of polymers. Okay, and that's another source of broadening of the molecular weights. Third and fourth generation of catalysts, Ziegler-Natta catalysts, are very similar between them. They are close to the second generation catalyst, which is magnesium chloride, titanium chloride, and aluminum alkene. But there are internal and external donors in both cases. In the fourth generation, is specified which are the external donors. We will see in the next slide what are these donors. Just for now, let's focus on the productivity. Third generation goes to 10 kilograms of pp per gram of catalyst. And your isotactic index increases up to 90%. You see, it's very important, the isotactic index, because if you are producing a quite large amount of attack polymer, you have to remove from your polymer before selling it, which means it's a very expensive and tedious process. Very expensive, most of it. So industry don't want that. Want to produce as much possible and with a higher isotactic index possible. And this kind of